Today we're starting section 4.3, using matrices to transform geometric figures. If you remember, transformations are translations, rotations, reflections, and compressions and stretches. So we're going to be using matrices to do this. Our vocabulary is we have translation matrix, reflection matrix, and rotation matrix, which we're going to define as we go through the lesson. First, to set things up, I want to talk about triangle ABC. The coordinates for this triangle are written there on the screen, and you can put these ordered pairs into a matrix. So you see your x-coordinates are the first row, the y-coordinates are the second row, and we're going to use this to work on a problem. A translation matrix is a matrix used to translate or slide coordinates on the coordinate plane. If you remember, the shape of the image doesn't change, it just moves around in the coordinate plane. So adding the original matrix, we're going to call that the pre-image, and the translation matrix gives us the coordinates of the translated image. So a pre-image, the original matrix, plus the translation matrix gives us the final image. First example, translate triangle ABC with those coordinates 3 units left and 4 units up. If you remember, left we're going to go negative, up we're going positive. Find the coordinates of the vertices of the image and graph. So first we're going to look at the translation matrix. The x is our first row, the y is our second row. So in the x direction we're moving left and right, but in this problem we're moving left, so I'm putting negative 3. The y direction we're moving up, so it's positive 4. So I have our pre-image, which are the coordinates of the triangle written in the problem, plus the translation matrix, is our translated image. So negative 2 plus a negative 3 is negative 5. 3 plus a negative 3 is 0. 0 plus a negative 3, negative 3. 1 plus 4 is 5. 2 plus 4 is 6. Negative 3 plus 4 is 1. So we have our translated image, the x coordinate and the y. Let's graph it. And it's already graphed for you. We have the pre-image and then the translated matrix. Okay, you try this one. Translate that triangle with those coordinates. 3 units right and 1 unit down. Remember, right is positive, down is negative. Find the coordinates of the vertices on the image and graph. You see there, we have the vertices of the translated image, and I'm going to turn the page and graph it. Okay, there we go. The pre-image is in blue, the final image is in red, and just because I can't draw straight lines on my iPad doesn't give you an excuse not to use a straight edge on your paper. Thank you. Alright, example 2, using matrices to enlarge a figure. A dilation is a transformation that scales or enlarges or reduces the pre-image. That's like the compression and the stretching. So we result in a similar figure. Remember that for similar figures, the shape is the same, but the size may be different. Angles are congruent and side lengths are proportional. When the center of dilation is the origin, multiplying the coordinate matrix by a scalar gives the coordinates of the dilated image. You remember, a scalar is just something you're multiplying by everything inside the matrix. In this lesson, all dilations assume that the origin is the center of the dilation, so it makes it really easy. Okay, enlarge triangle ABC with those coordinates by a factor of 2. So 2 is our scalar, multiplied by x is the first row, 2, 1, negative 3, y is the second row, 3, negative 2, 1. Our new matrix is 4, 2, negative 6, 6, negative 4, 2. We're going to use that to graph on the next page. And there you see your pre-image, the smaller one, and the final. So the final would be bigger than the pre-image because you multiplied it by a scalar of 2. Alright, you try this one. Enlarge that triangle with those coordinates by a factor of 4/3. Find the coordinates of the vertices of the image and graph. You guys do your best. I know it's a fraction, but fractions are your friend. Okay, check out the answer. You see I did improper fractions and I changed it to mixed fractions because mixed are going to be a lot easier to graph. And let's try to graph it. Okay, there you go. The pre-image is blue and the final image is in red. Next example, a reflection matrix. It's a matrix that creates a mirror image by reflecting each vertex over a specified line of symmetry. To reflect a figure across the y-axis, we're going to multiply this matrix by the coordinate matrix. This reverses the x-coordinates, which is red, and keeps the y-coordinates unchanged. So if you get a problem that asks you to reflect a figure across the y-axis, this is the matrix you have to multiply it by. And I wanted to remind you that matrix multiplication is not commutative. So be sure to keep the transformation matrix on the left. So you write the transformation matrix first and your coordinate matrix second and do your multiplication. Let's try one. Reflect triangle PQR with coordinates given across the y-axis. Find the coordinates of the vertices of the image, then graph. So here the instructions say to reflect across the x-axis, multiply by that matrix. So reflect this triangle across the x-axis, find the coordinates of the vertices of the image, and graph it. You try on your own. So if you see here, the x-coordinates have stayed the same and the y-coordinates have gone opposite sign. So now I'm going to turn the page and graph it. And there you go. The pre-image is in blue and the reflected image is in red. Example 4, rotation matrix. A matrix used to rotate a figure. Use each matrix to rotate the polygon ABCD with coordinates given about the origin. Graph and describe the image. When it says describe the image, that means we're going to say which way it rotated and how many degrees. So let's try one to figure it out. Multiply these. Hold on. If I multiply these, 0, 0, negative, I'll just write it out. 0 plus a negative 1, 0 plus 4, 0 minus 1, and 0 minus 3. It's our first row, over and down, so 0 plus 0, 2 plus 0, 5 plus 0, and 2 plus 0. Okay, do that addition, and I'm left with negative 1, 4, 1, negative 3, 0, 2, 5, and 2. Okay, I'm going to turn the page, graph the pre-image and the rotated image, see what happens. Okay, I'm going to go ahead and pause and graph because I know you guys know how to graph, so you don't have to watch that happen. So there's the pre-image. Now I'm going to graph the rotated image in red. Okay, if you look at the rotated image, I mean, if you follow, it actually has rotated. Let me change colors here. This way, which is counterclockwise. And it rotated 90 degrees counterclockwise. Let's try another one. Use each matrix to rotate the polygon about the origin, graph, and describe the image. So let's do one more. Change pens. And this is going to be 0 plus 1, 0 minus 4, 0 plus 1, and 0 plus 3. Next row, 0 plus 0, negative 2 plus 0, negative 5 plus 0, that's a plus, sorry, and negative 2 plus 0. Okay, finish that addition. 1, negative 4, 1, 3, 0, negative 2, negative 5, negative 2. Okay, we're going to take this information on the next page and graph it. Okay, I'm going to go ahead and graph as it's paused. So here's our pre-image. I realize it's probably easier for us to see how it rotates if I label the vertices A, B, C, D. So let's go ahead and graph the rotated image in red. And at 1, 0, that's A. Negative 4, negative 2. 1, 2, 3, 4, 1, 2. That's B. 1, 1, 2, 3, 4, 5 is C. And D is 1, 2, 3, 1, 2. So it looks like we're rotating clockwise. Looks like we went that way. So clockwise 90 degrees. Excuse me. Alright, there's next page is one yourself. So go ahead and try this one. Use that matrice and rotate it about the origin. Okay, let's go ahead and graph the pre-image and the rotated image on the next page. So it looked like this one went counterclockwise, 180 degrees. That's all we have for today. We'll see you guys tomorrow.